Assalamualaikum and a very good morning. My name is Zakwan, UTP, Chemical Engineering, ID 2425245, and today I would like to present for research proposal defense with my FYP title, Modified PID Controller for Improved Control Loop Performance Under Uncertain Environments. So let's go. Let's go with the next agenda. So for today's presentation, I will present about the background of the research, problem statements, the objectives, scope of study, literature review, methodology, Gantt chart and milestones, and also the conclusion. All right, next, when we talk about currently, the world is currently moving towards IR 4.0, where in the IR 4.0, Industrial Revolution 4.0, we focus more on automation and machine learning, where in automation, we know that machines are replacing jobs which are normally done by humans that are repetitive and highly predictable. And according to McKinsey report, repetitive works which are highly structured and predictable make up to 51% of the economy, while the value reaching 2.7 trillion in wages. Next. So how do we control a process? How do we control or how do we do the automation? In the industry, especially in the chemical industry, we use PID controller, where PID controller, before this in the early 1960s, is used to replace the relay, which in the previously, the relay are used for controlling automation purpose. So PID controller, PID, is a control algorithm that consists of proportional, integral, and derivative coefficient, where you can see here, UT is the output of the PID controller. Then there is the proportional coefficient, the integral coefficient, and also the derivative coefficient. We'll see more on how this works in the literature review next. Okay, and how the process is controlled. In the industry, most of the process is controlled by control valves. And although control valves is a control valve is used to control fluid flow by varying the size of the flow passage. So usually when we control the flow system, let's say we are controlling the fluid, which is the liquid, I guess, we manipulate the flow passage, the area which is inside the control valve to control the flow rate. And inside the chemical industry, mostly the control valve is used to control flow. First one is flow, next is temperature, and also next is pressure, and also the level of liquid inside a tank, usually like that. And for temperature, usually we control the flow of hot fluid or also the cold water used for cooling or heating of the process stream. So let's go next with the problem statement. So what are the issues with the control valves? What are the issues with the automation? And currently, we have identified that when usually inside an automation or control loop, when we are dealing with control valves, there are problems regarding control valves, which are non-linearities. Especially when we talk about control valves, there are non-linearities such as backlash, hysteresis, and also stiction. We'll talk more about that in the literature review section. And next one, which is something that happens to the controller, which is oscillatory feedback control loops, which causes variability in process variable, which create lower quality products and have a lot of side effects or bad effects to the process stream. When we talk about oscillatory feedback control, 30% of the oscillatory feedback control are due to valve problems, which is a big percentage. More than 1/4 of the problem is about the control valves, and nearly 25% of frequent problems addressed by control loop performance are regarding stiction. We'll talk more about stiction in the next section. So just to inform that my study will focus more on stiction. So inside an automation for process plant, the main component of the control loop consists of controller, actuator, the process, and also sensor. Actuator, controller, actuator, process, and also sensor. So actuator, control valve is regarded under actuator. and sticky valve will have to be replaced. Usually, when we have a problem of sticky valve, it needs to be replaced either immediately or in the next scheduled shutdown. So as you can see here, this is the bar chart regarding the problems addressed by control performance monitoring, and we've seen that valve stiction regarding sticky valve is considered as second most frequently addressed problem. Even though the first problem is wrong tuning settings, we know in industry that tuning methods or wrong tuning methods can be solved by auto tuning. However, with valve stiction, it requires the change of valve or modifications to the PID itself. That's why that is my motivation towards choosing valve stiction and design PID controller to perform under the valve stiction nonlinearity. Okay, next. The objective of my research for FYP1 is to develop a PID-based stiction compensation methods to minimize the effect of stiction on process outputs. It means that the PID controller is able to perform well even though we detect there is a stiction inside the process. And next is to test and validate the performance of the proposed method using simulation case study. Right, my scope of study, the first one is about the control valve nonlinearities. So my first scope of study is to understand what are the nonlinearities inside the control valve, which I had identified several, which are deadband, hysteresis, and also static friction. The next one is identify the detection method for stiction. So the detection method which I had researched is the nonlinear principal component analysis, the neural networks variable reference system, and next one is to design and modeling of PID, which will be done through MATLAB and also Simulink. Okay, literature review. So mostly I'll talk about the control valve nonlinearities, stiction detection methods, understanding PID controller, including what are the methods to compensate for stiction nonlinearities for PID controller. So there are three types of control valve nonlinearities, which are deadband, which also called as backlash in the industry, hysteresis, and also stiction. So when we talk about deadband, in the process instrumentation, there is a deadband refers to the range through which an input signal may be varied upon reversal of direction without initiating any observable changes in an output signal. So as you can see in the graph here, this one depicts the deadband. So when we talk about deadband, it happens when we are, let's say we are controlling or turning the valve. However, there are no change in the output of the process. So something like we control the mechanical movement, the stem of the valve. However, the stem of the valve, when we control, it does not change the area inside the valve, which is used to control the flow. That is the definition of deadband. Next one is hysteresis. Hysteresis is a property of element evidenced by the dependence of the value output or the given execution of the output upon history of prior excursions and the direction of the current reverse. When we talk about hysteresis, as you can see here in the graph, the first one is the yellow line. The yellow line depicts an ideal control valve, so ideal linear control valve. However, if hysteresis happens, as you can see here, the input and the output, it seems like this. So let's say if we apply 40% of the signal, the output or the control valve only travels about 10 instead of the full 90, or instead of when compared to ideal, it delivers about 35 or to 40. So to easily define this is the deviation between the actual and also the ideal linear valve. And the next one, the main, is the stiction. So according to Instrument Society of America, stiction is a resistance the start of motion, usually measured as the difference between the driving values required to overcome static friction, upscale and downscale. So let's look at the graph here. By usually that band, which we had talked about earlier, happens together with stiction. So stiction is the short-term word for static friction. So when we talk about friction, there are two types of friction, which are static and also dynamic friction. And usually, before a valve is moved, it needs to overcome the static friction, and that's why sometimes it needs more than usual amount of force to allow it to move before it moves according to the dynamic friction. And this problem causes a lot of oscillatory feedback control problems inside the control loop. So my research mostly will be done to compensate this kind of nonlinearities inside a control plant, inside a process plant. Next one is the stationary detection methods. I had identified three, which is NLPCA, the neural network, and also VRS. So the first one is nonlinear principal method analysis. This equations between the shapes of the signal. So let's say we have a signal. The shapes of the signals are identified. So when we identify which is this a stiction or not? So usually it is done by using the operating data of the control variable controller output. So we compare within the control variable, and we compare between the control variable and also the controller output for the nonlinear principal component analysis. And the next method is using a neural network. Neural network is one form of artificial intelligence which consists of three layers. The first one is the input layer. So let's say if you want to know more, neural networks are used in face detection in our smartphones. So it is trained to learn to know about the patterns of the control system. So usually inside of the neural networks, we give an input. So let's say it is input about the data on process variable and also controller output. If there is a stiction, so we have an input layer, it will be processed through the hidden layer, and then it will go through the output layer where it gives an information to us or give us feedback that let's say this is a stiction. So in case of the input layer, if we give an input which is non-stiction and it identifies as stiction, we could give a backward propagation to give a feedback to the neural network, and it's sort of like teaching the neural network that this is not the answer. So this method is called backward propagation method, and it is considered under supervised learning. All right. The next one is the variable referencing signal. Inside the variable referencing signal, the slope of the, let's say, the control valve, I mean the PV and also OP, is calculated, and then is referred to the stiction index. Next, we'll talk more about PID controller. PID controller stands for proportional, integral, and derivative, and these controllers are designed to eliminate the needs for continuous operator attention. So usually in the traditional controller, the controller only consists of one of the coefficient, which is P. So for each coefficient, there are advantages and disadvantages. So let's say in a P controller usually is good for reducing offset and also simple design. However, the offset cannot be removed, and also inside the P controller, let's say when the error is 0, so the output of the controller would be zero, and hence can produce the continuous output. So let's say when we combine P and I becomes a PI controller, the advantage of the integral part of the controller is that it removes the offset. However, it removes the offset, so it will reach the it will reach the set point that we set on the controller. However, the disadvantage is that it takes a longer response time and may produce oscillation. And when we combine with the third derivative, the derivative term, we get a controller which is fast enough, which can perform better than a PI controller. However, the disadvantage is that it is quite more expensive and harder to tune or design. So let's go to the next slide. We have a graph on this, and we see the effects, the different effects when a step change is introduced inside. When there is a change or disturbance introduced into the control loop system, we see that the P controller we try to respond towards the disturbance. However, there is an offset. The PI controller is able to remove or reduce the offset or to eliminate the offset. However, it takes a longer response time, and PID controller is able to do the same as PI controller with faster response time. However, okay, that's all. All right, next one is, let's say one of the disturbance is the station. So the next part is to to present. I would like to present more about the methods which are used to compensate for station-based disturbance. So the first method is fuzzy gain scheduling of PID controller. In this method, we apply a fuzzy block diagram, fuzzy term inside the block diagram, which is used to tune the three gain parameters of KB, Ki, and also Kd, which are the coefficient of the PID controller at the runtime. So in this method, the self-tuning fuzzy inference system is used to always update the KB, Ki, and Kd of the PID controller. So from the results, it is shown that the FGS, the fuzzy gain scheduling of PID controller outperforms the classical PID controller for all exploit cases, effectively managing station-based oscillation in the control output. So during these 2 or 3 more weeks, in the next weeks, I will focus more on the compensation methods. And the next method to compensate for station-based problems are the two-move method. So inside the two-move method, we add a compensator to the controller. So for this method, the first move of this method pushes the valve stem to a steady state position, while the second state force the stem to stay in a steady state position. So we can see here, we know from the literature review that for static friction, we need more, what we call that as force to move, because the static friction is much higher than dynamic friction. So inside the two-move method, firstly, we apply a larger force for the valve, and then only we tweak the valve. So we reduce the force. It's not reduce the force, but apply a backward force to push the valve to a position which is set by the controller. So for an example, let's say we want the area to be at let's say 22 cm cube. So since there is a section, we apply force so that the area is open at 3 cm cube. So then only we tweak the system and apply a backward force or an opposite force to push the valve, so the only 2 cm cube of area is open for the control valve. All right. literature review, there is a I would like to compare between the backlash and stiction and also detection methods. So let's see here, the deadband usually it is hard to differentiate. Manually, it is possible to differentiate between deadband and stiction. However, in the model, it is quite hard to differentiate between deadband and stiction because usually it happens together. So let's revise a bit. That band occurs when we try to turn the valve and there's no change in the output. However, stiction occurs inside a static machine where we need to apply extra forces, and that usually causes slip jumps. Where let's say it changes the control output, it changes the process variable abruptly. And also, we had identified 3 methods to identify stiction inside the control valve, which are neural network, NLPCA, and VRS. So a bit of summary, inside for the control valve nonlinearity, we had identified 3, which are deadband, hysteresis, and also stiction. For the stiction detection method, we identified also 3, nonlinearity, principal component analysis, neural networks, and also variable referencing system. And also the next part is understanding PID controller and compensation method. We had go through with the PID controller, which is what terms which is used for PID, how they complement each other to give a perfect control, and also some of the compensation methods which are used to help PID controller perform better under stiction nonlinearity, which are the fuzzy gain scheduling and also the 2-move method. So these are the methodology of my research. The first part is the literature review, where in the literature review, I study more on the current researchers inside the industry, and also identify the types of nonlinearity identification method and also the compensation methods. So the next one is modeling and modification. So based on my studies on the literature review on the compensation method, I will try to model and modify the PID controller to anticipate and compensate for stiction nonlinearity. Next part is to test the performance. So firstly, I will introduce a non-stiction disturbance into the system to test the PID controller performance, and also compare between the methods that I found before and modeled before, so to test the performance of all of the methods. And also evaluation to analyze and compare the difference between modified and unmodified PID controller under stiction together with the documentations. And this is my Gantt chart. My Gantt chart is based on my methodology, where I divided into 4 sections, which are literature review, modeling and modification, testing performance, and also evaluation and documentation. For the modeling, I am determined to start the modeling by week 8 of this semester and finish by week 5 of next semester, and followed by the testing performance and also the evaluation and documentation, which is done throughout FYP I and FYP II. Okay, as a conclusion, for next after the RPD, PID controller modified to be able to compensate for stiction nonlinearities to be able to perform under stiction nonlinearities. So that is my focus for next after RPD. And here are my main references. References on the compensation methods for PID controller for stiction nonlinearity. And these are the references for other parts, so for the background study and also literature review. So that's all from me. I hope, yes, that's all from me. Thank you.